friends, now we are in the 6th class of time response analysis, and the 22nd question is the transfer function of a system is given as 100 divided by s square plus 20s plus 100. The system is, there are 4 alternatives given, and this question has been asked in GATE 2008. So the transfer function is given as Ts equal to transfer function is Ts equal to nothing but 100 divided by s square plus 20s plus 100. Now if we compare this transfer function by the standard second order transfer, the standard equation of transfer function for second order system, then what is the standard equation for of transfer function for second order system? The standard equation is, let me write, the standard equation of transfer function for a second order system is Ts equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. Now if we compare with this standard equation, if we compare the given equation with this standard equation, then we can find that 2 zeta omega n equal to 20 and omega n square equal to 100. Now from this we get omega n equal to 10 radian per second. Okay. Now if we put the value of omega in this, then it will be 2 zeta into 10 equal to 20. Now zeta will be nothing but 1. So now we have got the value of zeta. So zeta is 1. So the system will be, what will be the system? The system will be critically damped. It will neither be underdamped nor be overdamped. It will be critically damped, because for a system to be overdamped, zeta should be greater than 1, and for a system to be underdamped, the value of zeta should be less than 1. So the system is neither overdamped nor underdamped, but it is critically damped. So option number C is correct. Now the next question is, consider the feedback system shown below, which is subjected to a unit step input. The system is stable and has following parameters: Kp equal to 4, K1 equal to 10, omega equal to 500, and zeta equal to 0.7. And the question is asking about the steady state value of Z is. There are 4 alternatives given, and this question has been asked in GATE 2007. So let us denote the input point as Rs and output point as Cs. So let us denote this input point as Rs and the output point as Cs. Let us denote this, this is the process, and let us denote this process by Gs. So let us denote this process, this by Gs. Okay. Now let us try to make this again. So what will be the loop? So let us try to make. So the loop is like, here it is sigma here, and this one is K1 by S. Again here it is Kp. It is Kp. Now these two get added over here, and this point is Z. Okay. Now after this there is GS. Actually we have denoted this block, this whole block by GS. So it is GS. After that the final point is CS. Okay. Now this, there is a unity feedback, and this unity feedback is from here to here, and this is unity negative feedback. So it is RS. Now it is complete. So now there are two loops. Actually there is one loop, and there are two forward paths from this point. From this point there is two forward paths. So the equivalent of these two forward paths, because there are two forward paths, so and both forward paths are adding at the same point, so the equivalent of these two forward paths will be Kp plus K1 by S. So now we can write that this is equivalent to nothing but, so we can write here, this is equivalent to this one. This point is omega. Okay, let me write by black. So this point is omega. Okay, and these two paths will be reduced to K1 by S plus Kp. Okay, now this point is Z. Okay, and after that here it is GS. Okay, now this point is CS, and there is a unity feedback here. Okay, so this point is RS, and this point is RS, and this is unity negative feedback. Now we can consider these two blocks as single block, and if we consider these two blocks as single block, then the equivalent block will be, what will be the equivalent block? So equivalent block for this will be, for equivalent block, now if we consider these two blocks as a single block, then the equivalent block will be nothing but, it will be equivalent to what? This is sigma. Again this is point K1S plus Kp multiplied by GS. So this will be the equivalent block. Now it is again negative feedback. So here it is RS, and this is minus, and this is plus, and this is CS. Now we can calculate the transfer function. The transfer function by the formula for formula for closed loop transfer function. So in this case, the transfer function will be Ts equal to what? Ts equal to what is that? Cs divided by Rs, and Cs divided by Rs. That this is nothing but this will be act as GS for that. So K1 by S plus Kp multiplied by GS divided by 1 plus GS into HS. So 1 plus, this is G, this is the equivalent G for this block. So and HS. The feedback factor is, the feedback loop is having gain its gain as 1. So it will be 1. So now what will be the equation finally? So the equation will be like this. We can write here K1S plus KP GS. So now what is CS? What is RS? So RS is nothing but or we can write here by adding, after adding it will be K1 plus KPS, okay, multiplied by GS divided by S plus K1S here plus KP GS, because S will cancel out in numerator and denominator both. Now let me write this side. Now CS will be nothing but TS multiplied by, CS will be nothing but TS multiplied by RS. So it is TS multiplied by RS, and we have got TS as this one. And now what will be Z? So from this block it is evident that Z multiplied by GS is CS. So Z is nothing but CS divided by GS. So Z is nothing but CS divided by, or you can say ZS. ZS is nothing but it is CS divided by GS. Okay. So we can write Z as TS into RS divided by GS, and RS is the input, and it is given that the input is a unit step input. So RS will be 1 by S. So we can write here. TS is it is given. So and RS is 1 by S. So TS is K1 plus KPS plus KPS. Okay, and here it will be also K1 plus KPS. It is, I have written it wrongly, so K1 plus KPS will be here. So it will be K1 plus KPS multiplied by GS, okay, divided by S plus K1 plus KPS multiplied by GS. There is one more term. The whole term will get divided by, this is the term TS, this is the term TS, and RS is 1 by S. So this is the term RS multiplied by TS, and the whole term gets divided, this whole term gets divided by GS. So if we divide it by GS, so this GS will cancel out this GS. Now we are left with only, so let me wipe out here so that we can write. So now GS is nothing but, ZS is nothing but it is 1 by S multiplied by K1 plus KP S in numerator divided by S plus, in denominator it is K1 plus KP S multiplied by GS. So in question it is asking about the steady state value of Z. So now we have to apply the final value theorem due to Laplace for finding out the steady state value of Z. So let us denote the steady state value by ZSS. So ZSS will be equal to limit S tends to 0 SZS. So what will be limit x tends to 0, and we have calculated zs, so it is 1 by s multiplied by k1 plus kps divided by nothing but s plus k1 plus kp s gs. Okay, now these two s will cancel out each other. So what will be it? So it will be if we put s equal to 0, so the numerator will be left with k1, and in denominator this s will be, first term will be 0 and second term will be left with k1, because this s will make it 0, k1 g0. So k1 g0. Okay, now it is nothing but k1 will cancel out each other, so 1 by g0. Now what is the value of g0? So if we find out the value of g0 means at s equal to 0, so it will be 0 square plus 2 zeta omega into 0 plus omega square. So it will be nothing but 1 by omega square divided by omega square. So these two will cancel out each other, and now we are the final value is 1. So which of the given options are correct? So option number A is correct one. Question is RLC circuit shown in figure. This is RLC circuit, and the question is saying that for a step input EI, the overshoot in the output E0 will be. This question has been asked in GATE 2007. So let us see which option is correct. So the given circuit in Laplace domain will be. So the given circuit in Laplace domain is, it will be, so EI will be transformed in EIS. Okay, EIS. RS will be as it is, so it will be 10, and for L it will be LS, so it will be SL. Okay, this will be R, so R will not change, so R will be as it is. So now, and C will be changed by 1 by CS. This will be 1 by CS. Now this will be, this is the output voltage, so output voltage will be changed E not S. Okay, now if we take the current flowing as IS, then IS will be given by, what is IS? IS will be nothing but it will be EIS divided by R plus SL plus 1 by SC. Okay, now if we add these terms, then it will be SC here S square LC plus RC S plus 1. So it will be nothing but CSEIS divided by LC S square plus RC S plus 1. If we take LC as common, then it will be LC, and here it will be S square plus R by L, because C will cancel out, plus 1 by LC. Okay, now this C will cancel out this, so now we are left with SEIS divided by L S square plus R by L S plus 1 by LC. Okay, now since it is given that the input is a step input, so this will be EIS will be nothing but 1 by s, and we have to find out the value of E naught. So E naught will be, so this E naught s will be, the output E naught s, this will be nothing but IS multiplied by 1 by CS. So 1 by CS multiplied by IS. So what will it? So it will be 1 by CS multiplied by IS is S EIS, okay, divided by L S square plus R by L S plus 1 by LC. Okay. So now S will cancel out each other. Now it will be 1 by LC EIS divided by S square plus R by L S plus 1 by LC. Okay. Now we have got the value of E naught s. So the transfer function will be nothing but E naught s divided by EIS. So if we put the value of EIS as 1 by s, and if we put the value of all the terms L, C, R, then how much it will be? Then it will be what is L? L is 1 millihenry. So it will be 1 by 1 millihenry means 1 into 10 to the power minus 3. How much is C? C is 10 microfarad. So if C is 10 microfarad, so it will be 10 into 10 to the power minus 6. Okay, and this is EIS divided by S square plus what is R? R is 10 ohm. So R is 10 divided by L is 1 millihenry. So 1 into 10 to the power minus 3. Yes. And what is LC? So LC is again 1 into 10 to the power minus 3 multiplied by 10 into 10 to the power minus 6. Now if we write this side, then E naught s, then transfer function Ts equal to E naught s divided by EIS. This will be nothing but how much it will be? So it will be 10 to the power 8 divided by S square plus this will be 10 to the power, it is 10 to the power minus 3, 10 divided by 10 to the power minus 3 because it's R by L, so it will be 10 to the power 4, 10 to the power 4 S plus 10 to the power 8. Now if we compare this with the standard equation, so how much we will get? So if we compare with the standard equation of second order system, what is the standard equation? So comparing with the standard equation of second order system, what is the standard equation of second order system? The standard equation is Ts equal to omega n square divided by S square plus 2 zeta omega ns plus omega n square. This is the standard equation. So let me wipe out here so that we can write. Now the standard equation is this one. So if we compare these two equations, then we get omega n square equal to omega n square equal to 10 to the power 8, and this will give omega n equal to 10 to the power 4 radian per second. Okay. Now 2 zeta omega n is nothing but 10 to the power 4. So 2 zeta omega n is again 10 to the power 4, and if we put the value of omega n, which is 10 to the power 4, so it will come, this will give zeta equal to 0.5. So since zeta is 0.5, so now the overshoot will be, so the percentage overshoot will be, the percentage overshoot will be how much? It will be 100 multiplied by e to the power minus pi zeta divided by under root 1 minus zeta square. So if we put the value of zeta as 0.5 and calculate it by calculator, then it is coming 16. So the percentage overshoot will be 16%. So it will be 16%. So which option is correct? So option number C is the correct one. Question is RLC circuit shown in figure. This is RLC circuit, and if the above step response is to be observed on a non-established CRO, then it would be best have the EI as a. There are 4 alternatives given, and this question has also been asked in GATE 2007. So the data is same as the previous question. So in the previous question, we have calculated the frequency of response, the frequency of oscillation, the frequency of natural oscillation. In fact, you can say as omega n equal to, the omega n was 10 to the power 4 radian per second. So according to the previous question, the you can say time period equal to, the time period was t equal to time period of oscillation t equal to 1 by omega n. So 1 by frequency, and what is here omega n? So omega n is 10 to the power 4 radian per second. So what is omega n? Omega n is 2 pi f. So from here we can calculate 2 pi f equal to 10 to the power 4. So f is nothing but 10 to the power 4 divided by 2 pi. Okay. So 1 by f will be nothing but, it will be 1 by 10 to the power 4 by 2 pi. Okay. So it will be 2 pi by 10 to the power 4. Okay. So what is the value of 2 pi? So 2 multiplied by 3.14, okay, divided by 10 to the power 4. So it will be nothing but 6.28, so 0.628 millisecond. So we can write here 0.628 millisecond. Now we have calculated the frequency of oscillation as 0.628 millisecond. So now we have to calculate the what type of input we should give, so that the response should be clearly observed on a non-storage oscilloscope, because it is given that the oscilloscope is a non-storage oscilloscope. So to observe the response of the system clearly, what should be the value of the input? It cannot be a step input, because for a step input it will stabilize and we cannot observe the transient response. It will stabilize and it will show the final, the steady state value only. So the option number A is not correct. Let us calculate option number B, C and D. So if it is a square wave of 40 Hz, 50 Hz, so the time period will be, so case 1, let us write here case 1. Case 1 is a square wave. a square wave of 50 hertz. So in this case, what will be the time period? Time period, let me denote time period. Time period as T1. So T1 will be 1 by 50. So it will be nothing but 10 to the power 3 by 50 millisecond. So what will be it? So it will be 20 millisecond. So time period is here 20 millisecond. Now case 2, when it is 300 hertz. Case 2. Case 2 is a square wave of 300 hertz. A square wave of 300 hertz. So in this case, time period, let us denote it by time period by T2 here. Time period T2 will be nothing but 1 by 300. This second, this much second. So it will be 1000 by 300 millisecond. So it will be about 3.33 millisecond. Okay. So it will be about 3.33 millisecond. And in case 3, it is a square wave of 2 kilohertz. A square wave of 2 kilohertz. 2 kilohertz. So here the time period T3 will be time period T3 will be, how much it will be? 1 by 2 kilohertz. It will be this much second. So if we convert it in millisecond, then it will be 10 to the power 3 divided by 2 into 10 to the power 3. That means it will be 0.5 millisecond. Okay. Now, if we draw the square wave here, if we draw the square wave, here, then it will be like this. And our frequency of oscillation will be, if we want to see the frequency of oscillation clearly, then it should be like that. Here also in opposite, it should be like that. So it is clear that the natural frequency of oscillation, this is the natural frequency of oscillation. Okay. So the natural frequency, and this is the square wave. This is the square wave. So this is the time period T for a square wave. So this will be the half of time period T for a square wave. So let me write it as T and this as CT, or you can say E naught T. So E naught T. So which one is E naught T? This one is E naught T. This one is E naught T. Okay. Now this point is half the time period of a square wave. This is half the time period. Let me write it clearly. Half the time period of a square wave. So from the figure we can see clearly that, let me write this side, the half half of the time period of a square wave must be greater than the time period, means capital T, time period of natural frequency of oscillation, time period of oscillation of the response. So time period of oscillation of response should be less than half the time period of a square wave. So let me write here. So time period of oscillation of time period of oscillation of response should be less than half the time period of a square wave. Okay, that is, now the time period of oscillation of response is 0.628, and if we do the half of these time periods T1, T2, T3, because these all are a square wave, so it will be this will be 10 millisecond, this will be 1.666 millisecond, and this will not be eligible because this is less than this is less than 0.628. So that is we can say that T should be less than what? This T, this is T. T should be less than T square by 2, where T square is the time period of oscillation of a square wave. So now let us check for T, in place of T square, let us check for T1, T2, T3. So T3 will not be eligible because T3 itself is less than T itself. And what about case 1 and case 2? So case 1 and case 2 is in case 2, in case 1 the time period is 20 millisecond, which is much greater than the time period of oscillation. So in this case, what will happen? We will see a spike, and the graph will you can say the response will be we will not be able to see the response properly because it will be very it will be compressed very it will be like this. You can we can make here the response will be like this. In case 1 the response will be like let me show here. It will be like the response will be like, let me show the response by, it will be like this. So we will not be able to see it properly. It will be a spike. The response will look like a spike only, and we cannot analyze the response properly. So the half the requirement is the half of the time period of a square wave must be comparable with it must be greater than and must be comparable with the time period of oscillation of you can say response. So this one is because T2 by 2 will be equal to how much? So it will be equal to 1.666. So it is also greater than 0.628, and it is also comparable with 0.628. So this one will be the most appropriate to show the response, because in case it is too much large, so we will see only a spike. Here it is too much less, so we cannot see the steady state response properly. So the appropriate response will be case 2, and so which one is correct? a square wave of 300 hertz. So option number C is the correct one. Now at the last of the lecture, I would like to share one of the most important thing to you people, that if you like my video, then you must subscribe my video, so that there is no need to search out new video. Automatic update will come if I upload the new videos. What you have to do, it is very simple. There is a circular logo coming in right of me. You have to just click on that to subscribe.